I was playing back the previous session before I sliced it up and sent it off to YouTube, and I noticed I made quite a few bloopers, mistakes. For one example, I used the word cyclic instead of using the word abelian, which is what I meant to say, but it just came out cyclic, and I was unconscious of that. Also, at one stage, I was within the context of talking about a group of order 6. I was thinking order 4. So some of the sentences I was saying were just garbage. Now I know there are professors who deliberately, consciously put mistakes into their lectures to keep their students on their toes. I don't do that. I don't need to do that. I make enough what the Americans call thinkos, which is sort of equivalent to a typo, so a glitch in thinking. So I don't need to. I don't need that policy. So if you're studying seriously these lectures, then pay attention to the possibility that from time to time your professor, I, make mistakes. Okay. All right. So this will be the second theory session, and you can see quite dense. One of the beauties of having this new board is I can put a lot on it, and because the camera's closer, you can actually read it all now. I have a look at the videos. I can now read this stuff, which is a huge improvement on the old one with its silver scratchings and so on. All right. Okay, so we're doing all the various non-isomorphic types of group that there can be, up to including order 8. Now, previous session we did 1, which is the trivial group, and then the prime ordered groups, so 2, 3, 5 and 7. That left 4, 6 and 8. So we did 4 and 6. And now we do 8. And you'll find the reasoning behind talking about G8, where 8 is just the order of the group. You'll find a lot of the reasoning for this one, G8, very similar to that of G6. So I hope you followed the previous session, studied it closely, because you'll need that knowledge and the techniques for this one. Right, G8. So let little g be any order of your group, and let's assume that the order of this element is 8. Okay. So once you have that, that means that this little g is a generator of the group, and therefore this group is of this kind. It's a cyclic group, right? So Ga is cyclic. Now you will always have a cyclic group for any integer n. So your g of n, the group of order n, will always have at least one type of group, and that's the cyclic group. Okay, so G8 is cyclic. So that's one type. All right. Now let's assume now, and we're sort of similar reasoning to when we're talking about G6. So there's a certain familiarity here. All right. Now let's assume that all the elements of G8 that we're talking about of order 2. Okay. Now, if we do not have an element in this group of order 8, then their orders must be 1, 2, or 4. Right? That's from theorem, what was it, 49, I think, that the order of an element divides the order of the group. Very important theorem that we use here, a very powerful tool. Okay? So if the order is not 8 of the element, of an element, then it's either 1, 2, or 4. Now forget about 1, that's just the trivial group. Assume that's done. So the order of our elements will be either 2 or 4. So let's now do the case where all of the orders of the elements are 2, except for the unit, of course. There's always the exception. Alright, so if they're all of order 2, then you can use theorem 38, which says that you can your group is then isomorphic to this form. So if all your elements, except the unit, have order 2, you can write your group in this form. It'd be isomorphic to this form. Now, in this case, when we're talking about G6, we tried this, but we got a group of order 8, but we're talking about G6, so there was no, it did not fit. But in this case it does, because we have 8 elements in our group, we're talking G8, okay? And if all the orders of the elements are 2, except the unit, it does fit, because the order of the right hand side here, this group is 2 by 2 by 2, that's 8, so that actually matches. So another possibility, another type of group, is of this form. Okay, so it'll be cyclic 2 times cyclic 2 times cyclic 2. So you've got a kind of double direct product. You've got 2 direct products. So that's another kind. So you've got G8 is cyclic, and here's a second possibility, a second type of group. And this is not isomorphic with that one. They're two different, they're different structures, different group tables. They are not isomorphic, right? Right. So what does what will the group table look like? In this context, when all the elements are order 2, let's we can use theorem 37, which says you have a minimal generating set. There's a bit of revision. Go back to theorem 37 if you're forgetting about this. But in the context where all your elements, except the unit, have order 2, then you can create a minimal generating set of elements. This is just a subset of your of the elements of your group. Okay, so 3 will be enough. Why is that? Well, can you remember that any element of your group can be written in this form using the elements, the members of your minimal generating set. That's the smallest number of elements you need. Writing in this form to be able to generate every element of your group, right? And these powers here, these integer powers here, they're either 0 or 1. Okay, that's revision from theorem 37. Okay, so this integer here can be either 0 or 1, 0 or 1, 0 or 1. So you've got 8 possibilities. So it fits because we're talking about a group G8. Okay. And so what are those elements? What are those 8 elements? Well, this can be 0 to 1. If it's 1, you've got an A there somewhere. And B can be 0 to 1. So if it's 0, there's no B in your term. So you have 2 by 2 by 2, 8 possibilities, and here they all are, right? So for example, ABC, you'd have 1, 1, 1 here. And for AB, you'd have 1, 1, 0. And for CA, you'd have 1, 0, 1, and so forth. Right? So that form generates all 8 possibilities, and that's theorem 37. Okay, so the actual table. So here are your elements of your group, and so here see the table C2 by C2 by C2 and the arrow. So it's here, this one. Now it's you can imagine it took me quite a while to write all these out, rather boring. Now because it's rather tedious, I did not make the effort to actually check the contents of these group tables. Now from experience in the past, when the group tables were a lot smaller, I did actually check, actually did the detailed study calculation of each entry in the group table for earlier group tables, and I was consistently finding errors in Barnard's book. So now this time, with so many entries and 3 times, I did not bother to check each one because it'd take hours and hours of rather boring work. So given Barnard's track record, I wouldn't be at all surprised that there are actually errors in these group tables. Now, the editors, the literary-minded professional editors of the publishing company that published Barnard's book, those literary types would not have the mathematical understanding to be able to check this. So if Barnard and his co-author are a bit lazy and didn't check, then it's quite possible there'll be errors here. So be warned. Okay, so if you do go into the nitty-gritty, actually checking each one to see if it's correct or not, don't be surprised if you do find errors, because that's Barnard's track record. I found quite a few errors in the past. All right, so I just copied these out of the textbook. If you don't have the textbook, this is the group table for C2 times C2 times C2. Okay? It's of that form. Now, to get the answers in this form, you'll probably have to do quite a bit of algebra. Now remember, each of these elements is of order 2, right? So, for example, that would mean, say, the inverse of this one, BC, would be itself BC, because it's order 2, and so on. So you may have to do quite a bit of algebra to like, for example, let's do that. So AB times AB is E. So you'd have to do some algebra to show that that's the case. Or it's another non-trivial one. So ABC times ABC is E. Well, that's pretty obvious, because ABC, all of these elements have order 2. Right. Okay. So we now have 2 different types. Okay, now eliminate. So we've eliminated for order 8. Here we assumed the non-unit elements are all of order 2. So that covered that case. Now let's do. We're being systematic. Now let's take the case where at least one of them, of the elements, has order 4. Right? So you can only, if it's not 8 and it's not 1, the order that an element can have, by theorem 49, the order of an element divides the order of a group. Right?